All right. We made it to section 3.9, one of my favorite parts of Calc 1, related rates. Ooh, some people don't like it. It's a little confusing. So I broke this up into parts. This first one is an intro to it. We're going to do like 3 different problems together. I'm going to do one, you'll do one, and then we'll do one together. And that's it for the video. Basically, in calculus was invented because they were studying dynamic systems. That is, measures that are related to each other, and as one changes, the other changes. But then you can have multiple variables. So, for example, there's the gas constant, there's pressure, volume, and temperature, and how they relate together. There's 3 variables there. There's all kinds of science applications to this. So, if you have basically the game is, if you know the rate at which different variables are changing, you can actually compute the rate at which the one unknown rate is changing as well through this method of related rates. If you look on page 247 in the text, he basically outlines, and so these steps right here, 1 through 7, etc., or whatever, are the same steps that everyone uses. Basically, you're supposed to read the problem carefully to understand what's being asked. So read it, understand it. That takes a little bit of time, so be chill about that. Just kind of, okay, it takes time to digest what's going on. The problems we're going to do, not so much. It's really more the technical side, but as we get into part B of this section, it'll be more like, wow, okay, I got to really stop and think. Sometimes I do this all the time. I'm a visual kind of guy. Diagrams are very useful, and it's also good to know some of your formulas from geometry, as you're going to find out. Basically, the next step is choose variables to stand for the unknowns in the problem, whatever they might be. The crucial step right here is come up with that relationship between all the variables. Okay, just come up with that good relationship. Once you have that, the rest is gravy. You're just basically, to find out the rates of change, you have to implicitly derive the equation, whatever you have, with respect to your independent variable time, okay? We've been doing that a few times now, so that shouldn't be too shocking. From that, you have to deduce in step 5. This sometimes can take some time, not tonight, not on this lecture, but it can take time to figure out what is the value of all the unknown variables at that moment in time where I'm supposed to find the rate at which this particular variable is changing. Yeah, so you have to do stuff like that. But if you've already done step 3, I've got the relationship, I can figure it out. Okay, so let's get to this thing. Finally, what you do is you plug the numbers in, you solve for your answer, and of course tell yourself, let's be patient. All right, so here's our problem. I'm going to do the rectangle. You guys have the fun of doing the trapezoid on the next one, and then we'll do one together. It has to do with a snowball. Okay, so the dimensions of a rectangle. Let's draw one in. Remember, diagram. I know there's a length. No, not that one. That's the length. It's about to erase with my finger like on a whiteboard. And that's the width. Okay. The length is growing at a rate of 6 inches per second. Let's circle that. While the width, 1.5, it is actually shrinking, growing. There's differences there. Find the rate at which the area, this is what you're supposed to find. Find the rate at which the area is changing precisely when the length is 22 and the width is 14 inches. That's a lot of numbers, and it freaks people out at first. But I'll just say this, forget all that stuff. What's the relationship between area and the length and width? It is area is length times width. So this notorious step number 3, crucial step, was actually for this one not hard. But here's the process, okay? This is how they're related to each other, okay? But we want the rate of change relationship. That is to say, we want the derivative. We want to see those derivatives with respect to time. So we take this equation, what did I say up here? We implicitly derive. Now here's the thing that's kind of cute. On the last one we did in a previous lecture, the width was held at 12. This time the width is also changing. So we're really looking at 1, 2, we're looking at 3 different variables, all changing with respect to time. The area, the length, the width. So if we implicitly derive, You erase that and write that in a note. We're going to implicitly derive this guy. Derivative. Implicitly derive. That's what we're going to do. Let's do it. On the left-hand side, guess what? dA dt. On the right-hand side, it's a product. And they're both live variables. Product rule. Wait a minute. Think about it. You can pause it and think about it. Product rule. So I go to the first guy, I derive L, and I just go, it's dL dt. Leave the second guy alone, remember? Plus, now I leave the first guy alone, times the derivative of the second with respect to time. This is your derivative level. This is your rate of change level right there. This is what we want right there. We love it. Okay, that's going to solve everything for us. But here's the thing. Now you're going to look at the numbers, and let's go from the start to the end. All right, the dimension of the rectangle will change with respect to time. The length is growing. The length is growing at a rate of 6 inches per second. So you know what I'm going to write over here? If the length is growing at a rate of 6 inches per second, I'll write dL dt, the rate of change of the length, is 6. Ooh. Read it. What do you think dW dt is? The rate at which the width is changing. It's, what is it? Negative 1.5. It's shrinking 1.5 inches per second. Okay. And finally, is that it? Yeah. What are we looking for? Well, we're looking for dA dt because it says the rate at which the area is changing. So we can start plugging numbers in. We can go dA dt is equal to dL dt, which is 6 times the width. Uh-oh, the width. Wait a minute. At precisely when these measures are true. So they're capturing it at a moment when the width is 14 and the length is 22. If you pick a different moment with different measures, you get different rates of change, different rectangles. So in this case, the width, we find out now, is that the width is 14, and by the way, the length they said is 22. And you see how you're plugging everything in? The width is 14, then the length is 22, and then dW dt is the negative 1.5. I will not bore you with the details, but what I got in this case is 51. 51 what? Go back to it. Inches per second, inches per second, inches per second. But this is an area. It's square inches per second. Ta-da! Okay. Pause. Contemplate. Moving on. This one's yours. So this is where, after you've got that one understood, pause your recorder, try this one on. You have got, in this case, 4 variables. Okay. Go. Coming back. Hi. The dimension of a trapezoid, the dimensions are changing in the following manner. The height is, okay, trapezoid. Here we go. There it is. There's the height. There's a base 1. There's a base 2. I don't care which is which. And then the area. Well, this is another one that, remember I said geometry might be important. Here it is. Here's that trapezoid formula. In fact, next semester in Calc 2, use the trapezoid rule for approximating integrals. You'll need this formula again, regardless. So this is our guy. And remember what I didn't even read the rest of the thing. But I know that there are all these numbers. But what I'm going to do next is I'm going to derive it implicitly with respect to time. So dA dt is equal to, oh my gosh, were you able to figure this out? Like that could be your first function. That could be your second. Again, product rule. Pretty good stuff. And the classroom is fun for me to go look at that and think about it and talk with you guys. So I hope that you're enjoying or understanding and thinking about these concepts. So we're deriving with respect to time. So it's 1/2 as a coefficient times dH dt. Leave the second function alone. Plus, leave the first one alone, 1/2 h. And now you derive inside the parentheses. Well, those are two different functions of time, b1 and b2. So we would say maybe dB1 dt, crazy, huh? Plus dB2 dt, and there you go. There's your formula. Now grab the numbers. What's this 1.2 all about? The height is the height is growing. dH dt is equal to 1.2. Next number, base 1. That's a number, but forget that one. Oh, here's one of the bases, base 1, is growing at a rate of 2. Okay. dB1 dt is 2. Keep going. Base 2, 1.4. Shrinking, though. Don't miss that. So dB2 dt is a negative 1.4. And you got them. But then you go farther. Hey, man, when it is 4 meters high, it's being tricky there. 4 meters high. So that means h is 4. Is it all meters? Yeah, good. And base 1 is 8. So B1 is 8. And B2, they told us, is 12. So you have something like that. This guy up here at the top is 8, this guy's 4, and this guy's 12. Okay, fine. At that moment, how quick is the area changing? This is a plug and chug, baby. It's dA dt is equal to 1/2 times what? dH dt? Oh yeah, that's 1.2. And then inside the parentheses, what's B1 and B2? Oh, 8 plus 12, okay. La la la. Plus 1/2, what's the height for? It's easy for me because I already solved it. And then what's dB1 and dB2? Well, dB1 is 2. Plus, but then dB2 is the one that's shrinking. It's a negative 1.4. And you can see it's just a matter of adding these numbers up. And I did this problem, and I got 13.2. Did you? And that's what? Meter second, meter second. This is area. Square meters per second, right? No, minute. Oh, I almost blew it. And that's it. Hope you did well with that one. One more. You can pause it. And it's like I don't teach this way, do I? I'm used to pausing. Okay, problem 14 I picked from 3.9. It has to do with the snowball. If a snowball melts so that its surface area, decreases at a rate of 1 centimeter per minute, there's that word decrease or shrink, find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay, it's a snowball. I'm assuming it's a sphere. How about you? I'm going to throw it at somebody, right? And the sphere, it's got a measure of a radius. And I looked it up. I'm not too proud to admit. The area, the surface area, I'll say it's the area. This is really the surface area of a sphere. Look it up. Okay, is equal to 4 pi r squared. Believe it or not. Now here's the thing. I got two variables, right? You don't have the problem in front of you, but I'll reread it for you. It says, find the rate at which the diameter decreases. The diameter. Do you see diameter in this equation? I see someone close to the diameter. I know that if you got a circle and you're going across, that's supposed to be a circle. The r and another r is equal to the diameter. So 2r is equal to d. So I'm going to get that r out of there by simply saying r itself is d over 2. I have to do that. That is a good point. Watch that one. Replay it again and again. If you don't have the variable you want in there, you have to find a way to sneak it in. And this is all pure geometry in this case. So in this case, we have a is 4 pi, not r. How about d over 2 squared? Ta-da! There's your relationship. We're going to derive it. You know what I'm going to do to make life easier? I'm going to clean up that right side. It's 4 pi times d squared. See that 4? I anticipated that happening. I just saw it. So really, a is pi times d squared. Okay, but what do we want? We want to derive it for the rate of change equation. Easy peasy, lemon squeezy. It is dA dt is equal to pi, which is just a scalar waiting to be done. Derive d to d. But he's a function of time. D is going to look silly. dd dt. Crazy, right? There it is. We have it. Okay, now it's time to plug the numbers in. Oh, the numbers aren't here, are they? The numbers are over here. It says the surface area is shrinking at a rate of 1 square centimeter per minute. So area decreasing at a rate of 1 square centimeter per minute. You know what that means in math talk? dA dt is -1, period. And it says precisely when the diameter is 10, at that moment when the diameter of the snowball is 10 centimeters. You know what that means? D is 10. That's a D. It looks like an A. D is 10. We can plug in. But look at dA dt is -1. He's over there this time. We've got pi times 2 times 10 times, the only guy we don't know is the thing we're looking for, the rate at which the diameter is changing. So I'm getting an answer. The rate at which the diameter is changing is actually a -1 over 20 pi, it looks like. Does it make sense for the diameter to have a negative rate of change? Think about it. Yes, the snowball is shrinking, therefore it's getting smaller, therefore the diameter is shrinking. And those of you that are word nerds, maybe I'm one too, this is approximately, and I think I got a -0.0159 roughly. It's approximately -0.0159. Now interpret that. We are working in centimeters. Yep. Centimeters per what? Minute. Old school would be that guy. Centimeters per minute. And that's the final answer to that one. Yeah, it's very slow. It's very slow. The surface area is shrinking very slowly and all that stuff. But it is shrinking. And we have got an exact answer. There you go. Done with another one. Enjoy studying.